Welcome to the deep dive. Today, we're plunging into something really crucial, a real-world application of AI and data, building a real-time AI fraud detection system.
Yeah, it's a fascinating area.
Our mission here is to take this detailed user guide, building a real-time AI fraud detection system with Spring Kafka and MongoDB, and, well, unpack how these cutting-edge technologies actually come together.
To see how they work in practice.
Exactly. We want you to understand how they create a system that can spot suspicious financial stuff almost instantly.
That instant part is key.
You're going to get some real aha moments, I think, especially around, why certain tech choices get made and how this kind of system balances speed with being accurate.
And it's just incredible seeing how this knowledge gets applied, isn't it? Taking these complex ideas and using them to solve a critical problem like financial fraud.
Yeah.
This deep dive really shows the power of integrating different text databases, messaging AI, into one cohesive solution that makes a real difference.
Okay, so let's jump right in then. We're talking about real-time fraud detection. Why is real-time so absolutely critical today? What's the big deal about spotting fraud the second it happens?
Well, it's pretty straightforward, actually. The speed of detection directly impacts how much money is lost.
Ah, okay.
In finance, every second counts,
Right.
right? If you don't catch fraud immediately, the damage is often done. The money's gone.
And hard to get back.
Exactly. Much harder. So monitoring transactions as they arrive lets you take immediate action. You might even stop a bad transaction right in its tracks.
Which is way better than the old way.
Oh, definitely. Way better than, constantly querying a database over and over. That's just too slow and inefficient when you've got tons of transactions flying around.
Okay, so given that need for speed, what are the main pieces? What are we actually building here, big picture?
So at a high level, you've got three core things working together. MongoDB Atlas Vector Search,
Okay.
Apache Kafka,
Right.
and AI-generated embeddings. The main goal is just to constantly analyze a user's transaction history and spot anything that looks, suspicious right away.
So building a pipeline to catch weird stuff instantly?
Pretty much. Catching
Oh.
anomalies the moment they pop up, not ages later.
Now, the guide gets specific. It lays out a 5-step pipeline. This is where you really see the data flow, right? Let's walk through that for everyone listening.
Absolutely. So it starts with step one, generating customer profiles.
Okay, what does that involve?
It means creating sort of synthetic users, fake users, but with predictable spending habits.
Ah, like a baseline.
Exactly. You store that baseline data in MongoDB.
Yeah.
It gives you a sense of what normal looks like for each user.
Got it. So we have the profiles, then we need transactions.
Right. Step two is produce transactions. You have a Kafka producer that generates these simulated transactions.
Like purchases and things.
Yeah, exactly. And for each one, it computes an AI embedding. We'll get to what those are, and then sends the whole package off to Kafka.
Okay, so the data hits Kafka. What's next?
Step three. A Kafka consumer then reads these transactions from Kafka and sticks them into MongoDB.
So that's how the data gets into the database.
Yep. That's the raw transaction data landing where we can work with it.
And now for the real-time bit.
Yeah, this is step four. The application starts to monitor in real time. It listens to something called MongoDB change streams.
Change streams.
Think of it like a live feed. It gets notified instantly whenever a new transaction arrives in MongoDB. No need to keep asking the database anything new yet. It gets pushed.
Ah, very efficient.
Critical for speed. Avoids that constant polling.
And finally, the payoff, the detection itself.
That's step five. Run vector search and detect fraud. As soon as a new transaction comes in via change streams, it's immediately compared against that user's history using MongoDB Atlas Vector Search.
And how does it decide if it's fraud?
The logic is specific. It's fraud if 1, no similar transactions exist for that user, or 2, any of the similar transactions that are found are already marked as fraud.
Okay, that raises a big question. How do you define similar?
Exactly. That's where the AI comes in.
Right. You mentioned AI embeddings earlier. What are those exactly? And how do they help find similar transactions better than just looking at the raw data?
So embeddings are basically numerical representations of data. Think of taking all the details of a transaction, user ID, amount, currency, merchant category, and converting them into a big list of numbers, like an array of floating point numbers.
Okay.
This system uses an OpenAI model, text embedding 3 small, to do that conversion.
And why is that useful?
Because it lets us compare transactions based on their semantic meaning, their overall vibe, you could say. not just checking if the dollar amounts match exactly.
So it captures more nuance.
Totally. It sees relationships and similarities that a simple data comparison would completely miss.
Okay, so these embeddings, these numerical vibes, are stored in MongoDB. How does MongoDB Atlas Vector Search use them then to find the anomalies?
Atlas Vector Search uses what's called a nearest neighbor algorithm. It's really good at finding documents, in this case, other transactions that are semantically similar to the new one coming in.
And it needs some setup.
Yeah, you configure a vector search index. The guide mentions setting num dimensions to 1536, which lines up perfectly with the output size of that text embedding 3 small model.
Makes sense.
And here's something really interesting. The choice of dot product similarity instead of, say, cosine similarity.
Why does that matter?
Well, cosine similarity focuses purely on the direction or angle between these numerical vectors, ignoring their length or magnitude. But dot product does consider magnitude.
And in fraud.
In fraud detection, magnitude can be a really strong signal, right? An unusually large transaction amount, or maybe a category that's way off for that user. Dot product helps emphasize these stronger deviations. It treats a big anomaly as more different than a small one.
I see. So it amplifies the weirdness in a way.
You could put it that way, yeah.
Yeah.
It's a subtle but potentially critical choice for catching real fraud.
That's a really powerful distinction. It sounds like a clever way to spot things that just feel wrong about a transaction, even if the individual bits look okay on their own. It's about the context and the size of the difference.
Precisely.
Okay, so to make this all happen instantly, you need some serious plumbing, right? Infrastructure. The guide highlights Apache Kafka and Spring. What do they bring to the party?
So Kafka is basically the central nervous system here. It's a distributed messaging system. It works on a publish-subscribe model.
Publish, subscribe.
Yeah, the Kafka producer publishes transaction events, usually as JSON data, to a specific channel called a topic. Here, it's the transactions topic.
And the consumer.
The Kafka consumer subscribes to that topic. It reads the events, deserializes them from JSON back into usable objects, and then stores them in MongoDB. It's the engine for getting that real-time data flowing at high speed.
The guide goes into Kafka configuration details, key serializer, value serializer, group aid, auto offset reset. That sounds technical. What does that stuff actually do for someone building this?
Let's break it down. Key serializer basically prepares the message key, often used for routing messages, into a format Kafka understands.
Okay.
Value serializer, super important. It takes our complex transaction objects and turns them into JSON so they can travel through Kafka.
Right, text format.
Exactly. Then group aid, that's for the consumers. It lets you run multiple instances of your consumer application together. They share the workload from the topic, which is key for handling lots of messages.
Makes sense for scaling.
Yeah.
And auto offset reset.
That tells a consumer where to start reading if it's new or lost its place. Setting it to earliest means it starts from the very beginning of the topic. Really useful for debugging or reprocessing all the data.
Gotcha. So these settings are crucial for making sure the data flows smoothly and reliably in real time.
Absolutely fundamental.
Okay, transactions are in MongoDB. How does the system know immediately to check for fraud without constantly asking the database? You mentioned change streams before. That's the key here.
That is absolutely the key. Change streams are, well, fantastic. They're a real-time feed.
A feed.
Yeah, the application can just subscribe, listen for changes like inserts, updates, deletes in a MongoDB collection.
So instead of the app polling,
The database pushes the updates to the application the moment they happen, like an event listener.
that sounds much better for performance.
Hugely better. It's essential for true real-time monitoring. And here, it's specifically set up just to listen for insert operations. Only new transactions trigger the fraud check.
Makes perfect sense. Okay, so we've got this robust system mapped out, but, every approach has limits. The guide points out a couple for this specific demo. What are they?
Yeah, the main one highlighted is that MongoDB Atlas Vector Search, at least as described here, does not support batching multiple queries.
Meaning
Each transaction has to be evaluated one by one. Sent off for vector search individually.
And the problem with that is?
Performance bottlenecks. If you're dealing with really high throughput, hundreds, thousands of transactions per second, doing them one at a time can slow things down. It might not scale to extreme volumes without some extra work.
Right, the demo works, but real-world scale is another beast.
Exactly.
So, thinking bigger picture, how do you get around that? How could you tailor this for, say, much higher transaction volumes or even faster detection? What are the alternatives?
Well, there are several really good strategies mentioned. One option is using MongoDB Atlas triggers.
What's that?
That basically moves some of the fraud detection logic directly into MongoDB itself.
Closer to the data.
Right. The benefit is potentially lower latency, and you offload processing from your main application.
Downsides.
Well, triggers have a hard time out, 30 seconds mentioned here, and they can be a bit less flexible for really complex rules compared to writing logic in your application code.
Okay, what else?
Another approach is to maintain a cache. Store recent transactions in your application's memory.
So you check the cache first.
Exactly. Reduces the load on the database for common checks, speeds things up. You could also run local similarity search. Use a simpler algorithm, maybe like cosine similarity, inside your application first. Filter out the obviously low-risk transactions before you even bother sending them to the more heavy-duty Atlas Vector Search. Saves resources.
Like a pre-filter.
Yeah, precisely. And finally, a very practical idea. Use a fraud likelihood score.
How does that work?
You assign a quick score based on simple metadata. Is the amount unusual? Is the merchant category weird for this user? Things you can check fast.
And then?
Then you prioritize. Only send the high-risk transactions for the full vector search analysis. Let the low-risk ones pass, or maybe do a lighter check. Optimizes where you spend your compute power.
So putting it all together, for a real-world system, it sounds like you probably mix and match these. It's not just one single answer.
Precisely. A hybrid approach is almost always the way to go for real applications.
Depends on your needs.
Absolutely. You have to weigh the trade-offs.
Yeah.
Are you optimizing for the absolute lowest latency? Do you need super flexible rules? Or is handling massive volume your main concern? You combine these strategies based on those specific needs. Understanding those trade-offs is paramount.
Wow, what an incredible deep dive. We've really unpacked how you can combine MongoDB Atlas Vector Search, Apache Kafka, and these AI embeddings to build a seriously powerful real-time fraud detection system.
It's a potent combination.
From, carefully creating those synthetic profiles at the start, right down to the nuances of choosing .product similarity, it's clear how much thought goes into these complex systems.
A lot of engineering.
And you've heard how individual transactions get processed and flagged so quickly, but also the smart ways developers can adapt and optimize things for the real world, always thinking about latency versus flexibility versus throughput.
It's that balancing act.
It really is a blend of cutting-edge tech and clever strategic design.
And this brings up a really interesting thought for you, the listener, to consider. How might these core principles, real-time anomaly detection, AI embeddings, continuous data streams, be applied beyond financial fraud?
Good question.
Think about it. Maybe monitoring network security logs for unusual activity? Spotting potential breaches in real time?
Yeah, I could see that.
Or even in healthcare. Imagine analyzing streams of patient data to detect early signs of disease much sooner. The underlying patterns, the architecture. It has incredibly broad applicability, really, across so many different fields. Something to think about.